Now we will see different strain measures. Okay. Before going into the derivation in the next lectures, in this lecture, let's see some strain measures in 1D case. So you must have heard of these different strain measures: engineering strain, true strain, green strain. So engineering strain, as we know all, it is defined as L minus L0. Sorry, L minus L naught divided by L naught. Okay, so change in length divided by original length. The true strain is defined as logarithmic of or natural logarithmic of L by L naught ratio. Okay, and in green strain, this is you might have heard or not so no aware of this strain measure. So there is a green strain uh, which is defined as 1 by 2 in bracket L square minus L naught square divided by L naught square. So this is also kind of a strain measure. Okay, strain measure can be anything. Okay, it is just a ratio of some change in length or and original length or current length. Okay, in this case it is the it is change in length squares. So this is also kind of strain measure only. So we will see in next lectures the derivation of strain measures, mainly the engineering strain measure for 1D 2D and 3D cases. Okay, so this is just kind of summary and to give a glimpse of different strain measures and its application. So engineering strain, as we know, it is used for basically linear elastic problems. Uh, okay, so it is used where there is a small strain and small displacement. True strain, or it is also called logarithmic strain. Okay, sometimes it is also called incremental strain. It is generally used in plasticity problems. Whereas green strain, it is highly useful in case of large displacement or rotational problems. That means the geometric nonlinear cases. For example, buckling. Okay, so this is an example of geometric nonlinearity. So in this case, green strain is used, and in hyperelastic problems also green strain is widely acceptable. The reason is that uh, we will see this in our hyperelastic lectures. Uh, Hyperelastic materials, if you are aware, they are defined they are defined in terms of strain energy function, strain energy density function, which is a function of some strain measures. So the research showed that the strain energy density is more compatible with the green strain measure. Generally, why it is used? So there is no much no physical interpretation or physical reason, but sometimes most of the times they are used based on convenience. Okay, so it is more compatible and convenient to use green strain for strain energy density function, and that is the reason it is used for hyperelastic applications. So let's focus on this true strain. Okay, why it is and we will see green strain, why it is used or why it is good strain measure for large displacement rotation in upcoming lectures, and why green engineering strain is only suitable, or it is not suitable for large displacement. Okay, it is only suitable for small displacement. So these things we will see later, but let's focus for now on the true strain. Okay, which is good strain measure, considered a very appropriate strain measure for plasticity. Okay, so logarithmic strain, as we said, it is suitable for plasticity because the plasticity material are path dependent material behavior. Okay, and the log strain. Okay, They are suitable for capturing true strains. True strain means they capture the current length, okay, current deformation status or current deformation length while capturing the strains. And the log strain is derived from taking incremental strain into account. So this is the reason no, it is suitable for capturing true strain because it captures incremental, it captures the strain incrementally so that we can capture that current length incrementally and update and add it into total strain. Okay, so let's see how it is derived. So incremental strain at, let's say, incremental strain at particular instant is d epsilon dl by uh, L. Okay, so L is current length. Okay, for example, let's take this is a strain. Okay, on different steps or incrementally. Uh, there is a deformation is happening, so we are measuring strain here, we are measuring strain here, we are measuring incremental strain here. Let's take for particular instant here. Okay, this strain, okay, as we know it is a small incremental strain which is equal to dl by l. Okay, so we are taking change in length for that instant divided by current length, okay, not original length. If we take original length, okay, then it becomes engineering strain. Since we are interested in capturing true strain, okay, or path dependent strain, we are taking current length, okay, dl by l, current length. So this is a incremental strain, and from start to this current, okay, this is total strain, okay, e total. Or so true strain, okay, which is as we said it is derived by taking incremental strain into account. So the total strain will be addition of all these incremental strains over this path. So true strain, we just take integration, okay, from original length to current length. So original length is L naught to current length L. So we are just taking summation or integration of that incremental strain over the path. So d epsilon, okay. So we'll just substitute d epsilon as dl by L here, okay, and we take integration. So we get this logarithmic strain measure. Okay. Now you can see in this formula, this integration is strain path, okay, and this one is incremental, and that's how we say the logarithmic strain is suitable for capturing path dependent strain, okay, or a strain path, and that adds incremental strain, okay, to find the total true strain. So we said true strain is incremental and additive, okay, and therefore it preserves the history of deformation and it is suitable for plasticity problems. Because we know the plasticity problems or plasticity material, unlike elastic materials which are reversible, okay, plasticity materials are irreversible, okay, like for example if we deform particular structure to some length, okay, there might happen some plastic strains, okay, there might generate some plastic strains, and the component or structure undergoes permanent deformation. Now for next increment of load, this permanent deformation which happened prior, okay, it will affect the next deformation, okay. So we say like the plasticity material is history dependent or path dependent material behavior, because earlier what happened, like plastic deformation or permanent deformation, it is going to affect the future deformation path. So hope this is clear. Now let's try to understand this with example. Okay, this is I have taken from a book by Nitin Gokhale. Okay, let's take there is a deformation is happening from 1 mm length to 2 mm. Okay, so we are stretching 1 mm rod, let's say example, rod of 1 mm, we are stretching to 2 mm. Okay. So if we take incrementally, if we calculate incrementally the strains, okay, let's say we are calculating the strain into three increments or three steps: 1 to 2, 1.2 mm, then 1.2 to 1.5 mm, 1.5 to 2.0 mm. Okay, so with these increments, okay, if we capture both engineering strain and true strain, okay, for first increment it is a zero point 0.2, right? So the difference of length divided by original length, zero point 0.2. For next increments it's 0.25, and third increment is 0.33. Okay, so when we add this all the strains, incremental strains, engineering strain measure gives us 0.78. Okay, whereas if we calculate engineering strain not incrementally, just from 1.0 to 2 mm directly, okay, so we get difference is 1.0 divided by original. Okay, so 1. So if we see, when we add we get 0.78, but when we calculate directly we get 1.0. Okay. On the contrary, if you see the true strain, logarithmic strain measure, okay, we are calculating it incrementally and adding it. Okay, adding it all these three, we get 0.6931. And when we calculate directly the true strain, okay, from 1 to 2 mm, we get log 2 by 1, 0.64 0.6931. So whether you calculate incrementally or direct, okay, we get same value of strain using true strain measure or logarithmic strain measure. Okay, so from this we can say, like, no, this this strain measure preserves the history of deformation. Okay? This preserves history of deformation. Okay, so whether we take small steps or large steps, or even if we take direct no, one big step, we get same amount of strain. Whereas law engineering strain, it doesn't preserve history of deformation. And as we know, plasticity is history dependent or path dependent material behavior. We generally, the true strain or logarithmic strain is appropriate measure of strain. So that's the logarithmic strain. Okay, and more on engineering strains and green strains we will see in upcoming lectures. Okay, so this is just one plot. Okay, where there is L by L0 is also called stretch lambda. Okay, this is also called stretch. The ratio of current length to original length is also called stretch. Okay, let's take a 2.0. And if we take strain measures, okay, this is engineering strain measure, which is delta L by L0. So when L by L0, we get engineering strain as 1, right? So it is a linear strain measure. So this engineering strain measure is linear strain measure. And that is the reason it can be used for linear static problems where there is a small deformation and small displacement and small strains. Okay, so these kind of problems we can use linear strain measure. Whereas if we plot uh, true strain and green strain, okay, I think this is reverse, this is wrong. This is our, this is green strain. Okay, this one by 2 L square, L minus L square minus L naught square divided by L naught square. Okay, so if we plot that and it can be seen that it is a non-linear strain measure. Okay, we get something like this. Okay, and it is always higher for small strain problems. Both are almost same. Okay, if we take small strain with this range, the linear strain measure and this green strain measure, okay, which is non-linear strain measure, both give almost same values of strain. Okay, but as uh, the strain is increasing, this is this reports higher values. Okay, and this is a true strain. Okay, or logarithmic strain. This is also non-linear strain measure, which is appropriate for plasticity problems. Okay, and yeah, so this is how it looks. Okay, for particular stretch, okay, from 1 to 2 mm, we can see the true strain reports lower strains, whereas green strain reports highest strains, and linear strain measure is somewhere in between. Okay, so in next lectures, we will start the different, not different, but we will start seeing the derivation of strain measures and different strain measures like nominal shear strain measures. We will see this for 1D case and extend our understanding to 3D strain measures.